everyone. Welcome you all once again. I'm Meghamala, working as an assistant professor in Electronics and Communication Department from Institute of Aeronautical Engineering. Coming to today's topic, we are going to discuss about the logical combinational logic modules part 2. So today's topic is combinational logic module part 2. So in the last class, we have discussed about combinational logic module part 1. In the part 1, we had discussed about different logical circuits, okay, in the gate level. So different logical circuits that we had discussed in the last class is multiplexer, demultiplexer and decoders. Okay, so we had discussed the gate level modeling by considering all these combinational logic circuits. Whereas here in this presentation, we are just moving forward with some more examples based on the logical combinational logic modules. Okay, so basically today's presentation will be discussing about encoders, different types of encoders, and magnitude comparator. Okay, so coming to the magnitude comparator. So this magnitude comparator is a combinational logic circuits where the output is being compared between the output that we are obtaining is nothing but the combination, or else the comparing two inputs. Okay, the comparison between two inputs is the we know that the inputs will be in the zeros or one, binary form, 0 or 1, but the output that we can compare with respect to the input. So the combination of the comparators are in three types: A greater than B, A is equals to B, and A less than B. That means what here we compares two digital or binary numbers in order to find out whether the binary number is equals to 1, greater than 1 or less than 1 with respect to the input. Okay, so we logically design the circuit by considering the two inputs A and B and the combination of three output. The comparator with the combination of three output comparisons will be done in three outputs: equals to B, greater than B, and less than B. Okay, so these are the conditions that we get in the output with respect to the input. So in the comparator, we had different types of comparators: 1-bit comparator, 2-bit comparator, 4-bit comparator, and 8-bit comparator. So coming to the 1-bit magnitude comparator, here a comparator used to compare 2 bits is called a single comparator. Usually 1-bit comparator is nothing but the comparator where it compares 2 bits is called single comparator. So it consists of 2 inputs, each follows with the 2 single bit numbers, and the 3 output generate, which is less than, equals to, less than, equals to, and greater than. Okay, between the 2 binary input numbers. And the truth table of this 1-bit comparator is here. So in this truth table, we have A and B and the conditions. Okay, so the conditions goes like this: A less than B, equals to B, and greater than B. So when the input's 0, 0, it means what? My input A is 0 and B is 0. So my condition I'm observing is here: A is equals to B. So A is equals to B is 1. Okay, it's not like A less than B. It also not like A greater than B, but it is A equals to B. Why? Because both A and B are 0. And coming to the second one, 0 and 1. Okay, A is 0 and B is 1. When A is 0 and B is 1, then here my one of the input is 1, that is my B is 1, right? So A is less than B. A is 0, obviously, which is less than 1. So A less than B. So here A less than B, 1. The rest will become 0. And next is 1 and 0. For these two input combinations, my output goes like this: A greater than B. So A is 1, obviously B is 0, which is 1 is greater than 0, right? So A greater than B. And then both when the inputs A, B are equals to 1, then equals to. So based on the inputs, the output conditions will be observed, okay, and taken out. This is a single bit magnitude comparator, where the single bit magnitude comparator consists of only a single bit compare 2 bits. When we compare 2 bits A and B, then we call it as a 1-bit magnitude comparator. Okay. So from the above truth table, the logical expressions also can be written. How is? For A greater than B, AB bar, and for A less than B, A bar B, and A equals to B, A bar B bar plus AB. Okay, these expressions will be written with the help of the truth table, and the truth table we obtain with the help of the given inputs and the condition which is matching with respect to the input. So here we have A less than B plus A greater than B is equals to so here A less than B, A greater than B. When we concatenate both, then we form as A bar plus AB bar. So the taking complements on both sides, this is what we observe, AB plus A bar B bar. So finally, when the conditions, when we take the complement for the given condition A less than B, concatenation of both the conditions A less than B and A greater than B, we will get a plain A is equals to B. Okay, so this is a simplification with respect to the combinations that we had considered by taking the complement. So this is all we will see in the 1-bit magnitude comparator. Okay, coming to the next one. This is a logical circuit which we had implemented with respect to the Boolean expressions that we got in the previous slide. So as per this, this is how we have to draw the circuit. So logical circuit A and B, A bar goes here, A less than B, and this is for A greater than B. Okay, and finally we got here expression as A equals to B. So A less than B plus A greater than B complement is A less than B plus A greater than B, which is equals to A plus B for the whole complement. So A less than B we have a NOT gate, and A greater than B we have a NOT gate, and concatenation of both these comes to and finally OR gate. Okay, so this is all about 1-bit magnitude comparator. Coming to the 2-bit magnitude comparator, we had seen in the 1-bit magnitude comparator, the inputs will be 2 and the outputs are obtained with respect to greater than, less than and equals to. When it comes to the 2-bit magnitude comparator, the inputs will be 4. So for 1 bit, the input is 2. For 2 bit, the input is 4. Okay, so here it compares number of each of 2 bit is called 2 magnitude comparator, and it consists of 4 inputs. It has 4 inputs, A1, A0, B1 and B0, and as usually it generates 3 conditions, less than 1, equals to 1 and greater than 1 combination. So the truth table for 2-bit comparator is here. So for this combination 0, 0, 0, 0. So all are 0, right? So for A0, B0, here this condition has been satisfied. And coming to the next one, A0, 0. Okay, that means A is equals to 0, but B is 0 and 1, isn't it? So B is 1. So somewhere around in B1 and B2, we have 1, right? So here in this combination A0 and A1, we have 0 and as well as 0. So it is 0 obviously, and B is 1. So the combination that we are satisfying is A less than B. Similarly, 0, 0, 1, 0 and 0, 0, 1, 1. Okay. So for this, as per this, these are the conditions we are getting with respect to the inputs. 0, 0, 0, 0. So coming to here, 0, 1 and 0, 0. Here 0, 1. A is 0, 1 and B is 0, 0. So when 0, 1, we have 1 in A, but we have all zeros in B. So here A greater than B. Isn't it? 0, 1, 0, 0. For this, A greater than 1 is satisfied. So such that here totally we have how many combinations? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. So for 16 combinations of input, we are getting the output with respect to greater than, less than and equals to. Okay, this is all about 2-bit magnitude comparator. Always remember, for 1-bit magnitude comparator, the inputs are considered to be 2 inputs. For 2-bit magnitude comparator, 4 inputs are to be considered. But the output in the output, the conditions are one and the same: greater than, equals to and less than. So coming to the truth tables. So here the truth table, from the truth table, see from this truth table we have from the truth table K map has been drawn. So this K map is nothing but the Carnot map. So this Carnot map will help us to write down the expressions in sum of products and product of sum. Okay, so this will enhance the given input in order to write the combinations with respect to the in order to write the expressions with respect to the truth table. So coming to the truth K map here, again considering the three conditions: A greater than B, A less equals to B, and A less than B. So here we have to write the combinations for 4 inputs: A1 A2, B1 B0, A1 A0, and B1 B0 with the combination 0 0 0 1 1 1 and 1 0 and 0 0 0 1 1 1 and 1 0. Okay, regarding this Carnot maps, already you have studied in the digital logic design systems. Okay, so it is like a gist that you can understand. I'm not teaching you in depth, but in general I'm just explaining you how we need to get the Boolean expression with respect to the Carnot maps, and how the Carnot maps have been drawn is with respect to the truth table that we obtain. Okay, so for 0 0 0 1, now we have to see the combinations. So here 1 and 1 are mapping, so it is of a pair, and here a quad is formed, and here one more pair is obtained. Okay, this is with respect to A greater than B. This how we got is for A1 A0 0 1 0 1 and 1 1, for A1 A0 0 1 1 1, for A1 A0 0 1 0 1 and 1 1. So for these two conditions 0 1 and 1 1, for these two conditions with respect to A greater than B, right? So with respect to A greater than B, yes and yes. So for A greater than B, for the combinations 0 1 and 1 1, we are obtaining A greater than B. So likewise I have given 1 1 over for 0 1 and 1 1 for A1 and A0. Similarly, when you observe for B1 and B0, so for B1 and B0, we have where 0 0 and 0 1, isn't it? For B1 and B0, 0 0 0 0 and 0 1. 0 1 is, this is 0 1, and here 0 0 is this one, same. So here 1 is obtaining and 1 is obtaining. Okay, so this is how the Carnot maps have been drawn. So after drawing the, and coming to the A equals to B from the truth tables, the combinations that I'm here in this A equals to B, nowhere I'm getting a pair, neither a quad. Okay, so only a single bit, I'm just single bit that we have observed in the condition for A is equals to B. And coming to A less than B, here we are getting totally one quad and one pair. Okay, 2 pairs, 1 quad and 2 pairs. Here 1 1 and here 1 1 and here 1 quad. Okay, so A less than B, again this has been observed from these conditions. Okay, A less than B by considering A1 and A0 and B1 and B0. So after drawing the Carnot maps, the next thing is we have to write down the logical expressions. The logical expressions will be observed from the Carnot map. So here for A greater than B, what are the combinations that we got? A1 B1 bar, A1 B1 bar plus A0 B1 bar B0 bar plus A1 A0 B0 bar. Okay, so this has been observed with respect to A greater than 1 from the Carnot map. Okay, so here see A1 bar A0 and here A1 A0. So here which one is coming common? I mean we can take common. A0 is been taken common. So likewise for A equals to B and also for A less than B. So for A is equals to B, we like these are the combinations. After simplifying, we are getting A0 XOR B0 and A1 XOR B1. So this is what we are getting for A equals to B. And for A less than B, simply A1 B1 plus A naught bar B1 B naught plus A1 bar A naught bar B naught. Okay, so always remember that we are obtaining this logical expressions with respect to the Carnot map, K-maps. Okay, so with respect to the K-maps, we are able to get these expressions, Boolean expressions, and how the Carnot maps have been drawn is with respect to the truth tables. Okay, so in the truth table, we have inputs and as well as the outputs. For 1-bit comparator, 2 inputs have been taken, considered. With respect to the 3 combinations, A equals to 1, less than 1 and greater than 1. For 2-bit combinations, for 1-bit combinations, 2 inputs, and for 2-bit comparator, 4 inputs. Okay, but the conditions at the output are same with respect to A equals to, less than and greater than. Same for outputs for 2-bit Mangroot comparator, greater than, equals to and less than. Okay, so after using this, we have to after obtaining the expressions, this Boolean expressions, the final stages, we have to draw the circuit diagram. So here in the circuit diagram, first of all, considering inputs A0, A1, B0, B1. Okay, and we have complements, right? So these are the NOT gates. For A0, A1 bar, A0 bar, B1 bar, and B0 bar. Okay, so with respect to for A less than B, this is a combination, right? So A1 bar, B1. So A1 bar and B1. A1 bar and B1. And what else? A0, B1 bar, B0. For less than, right? Sorry. A0 bar, B1, B0. So A0 bar, B1 and B0. Okay. So what else? A1 bar, A0 bar, B0. A1 bar, A0 bar and B0. So totally this one. What is this? A1 B1 bar, A1 B1 bar and A0 B1 bar, A0 B1 bar, B0 and A0 bar, B1, B0. A0 bar, B1, B0 and A1 bar, A0 bar, A1 bar, A0 bar and B0. Okay. So these are the AND gates. But because here we have plus, right? So AND gates, these are A1 dot B1, A1 into B1. So the OR gates and OR gates, combination of AND gates and finally given to OR gates, so that we are obtaining A less than B. Similarly, with A equals to B and A greater than B, using these expressions, this one and this one. So using these expressions, we are going to draw the circuit diagram. So this is all about 2-bit Mangroot comparator. And coming to the 4-bit Mangroot comparator. So for this 4-bit Mangroot comparator, we have the combination of 8. So here it has a comparator can use to compare 2 binary numbers, each of 4-bit. So here 1 bit, for 1 bit, 2 inputs, for 2-bit, 4 inputs, and for 4-bit, 8 inputs. 4-bit, each of 4 bits. So 4-bit Mangroot, each of 4-bit Mangroot comparator is been considered. So for 4-bit, 8 bits of inputs have been considered with the combination of same. A greater than 1, less than 1 and equals to 1. So here for this 4-bit comparator, condition for A can be possible in the following case. So for this, the condition for A greater than B, these are the possible conditions. 4 possible conditions can be observed in 4-bit comparator. And for A less than B, so these are the conditions that we can obtain using with respect to the A less than B condition. And for A equals to B condition, the possible only is all the individual bits of one number exactly coincide with corresponding bits of other. So for A is equals to B, all the individual bits, all the individual inputs are coincided with respect to the another number. So here in this A equals to B, we don't see any kind of combinations with respect to the input in between the input. So why? Because here the individual bits of one number can be coincided corresponding with respect to the another numbers. Okay, but this is what you have to remember for a greater than b, and these are the conditions for a less than b. Okay, these are the 4 cases you have to remember when it comes to the 4-bit Mangroot comparator. So here, by using the Boolean expressions, we can implement the logic circuits. So here, by using these expressions, we can implement the logic circuits, where here for a greater than b combination, we have A3, A0, A1, A2, A3, and B0 bar, B1 bar, B2 bar, and B3 bar. So it is a complement of B. Okay, and here complement of B, and here we see B1, B2, B3, and complement of A. Okay, but whereas here you see A0, A1, A2, A3. So A0, A1, A2, A2, and A3. Okay, each of 2, 2. So totally 8 inputs. So overall, for the complement of A greater than B, by using these combinations, I'm going to achieve the condition A greater than B. By using this combination, I'm going to achieve A greater than B. By using these combinations, I'm going to achieve A less than B. And directly with the combinations A0, A1, A2, and A3, B0, B1, and B2, and B3, I'm going to achieve A equals to B condition. So this is all about 4-bit Mangroot comparator. So till now we have discussed what is a comparator, what is a 1-bit Mangroot comparator, what is a 2-bit Mangroot comparator, and what is a 4-bit Mangroot comparator with respect to the inputs that we are considering in order to obtain the conditions greater than 1, equals to 1, and less than. Now, coming to the cascade comparators. What does this cascading mean? Not only in the comparators but also in the different combinational circuits, cascading can be done. Okay, when it comes to the hardware also, or else when it comes to the multiplexer, demultiplexer, decoder, and encoder, whatever the combinational circuits that you are considering, we can go for the cascading part. So we can cascade. Cascading is nothing but taking one more similar kind of the circuit and arranging with respect to in a parallel series or else in a series. Okay, so here a comparator, it performs a comparison operation for more than 4 bits by cascading 2 or more 4 comparators is called cascading comparator. So here this is what about a 4-bit comparator. So this is a comparator, 4-bit comparator, 4-bit Mangroot comparator. What am I doing is I'm cascading it with respect to the another comparator, another 4-bit. See here, if you observe, for this is a first comparator I'm considering. For this 4-bit, totally I'm having how many? For 4-bit, I should have 8 bits, right? So 8 bits with respect to the output, and that output is given as one more input bits to the second comparator. So likewise, I have cascaded 2. I have combined 2. So this is nothing but the cascading comparator. So when 2 comparators are to be cascaded, the outputs of the lower order comparator are connected to the corresponding inputs of the higher order. So the output of lower order, output of A0, A1, A2, A3 is being given as the corresponding inputs to the higher order. That means what? A11, A12, A13, A14. This is higher order inputs. This is lower order outputs. So this lower order output, we got it from first magnitude comparator and then has been given as input to second magnitude comparator, isn't it? So that is what the cascading comparator does. So what are the applications of comparator? I hope you understand what is a cascading comparator. Remember that higher order comparator, inputs of higher order, the lower order outputs can be given as input to the higher order comparator. Okay, so it is nothing but the cascading, the connecting. And coming to the comparator applications, the applications are goes like this. It is used in CPU, central processing units, and the microcontrollers. Okay, different types of microcontrollers like we have, and also they are used in control applications in which binary numbers representing physical variables such as temperature, pressure, and so on. So physical variables are nothing but the temperature, pressure, etc. So they can come in order to know the exact temperature, or else in order to know the exact value of the pressure, we can also implement these Mangroot comparators over here, okay, in the control applications. And also comparators are used as process controllers and for servo motor controllers. So not only in the physical, not only in the control applications, but also these can be used to control the process controllers and servo motor controls, and also used in password verification and biometric applications. This Mangroot comparator can also be used in the biometric applications, okay, and also in the password verification. So this is all about the Mangroot comparator. Okay, coming to the designing part. Now this all the examples that we had considered till now. Now we have to see in the gate level modeling how this Mangroot comparator acting or else it is being considered under how it is going to develop using gate level in the gate level modeling. Okay, so in this gate level modeling, as we all know, the design concepts 4-bit inputs. So 4-bit inputs means it is obviously it is a 4-bit means 2-bit Mangroot comparator. When the inputs are 4-bit, obviously it is a 2-bit Mangroot comparator, right? So it generates A and B and 3 output combinations equals to greater and less than, equals to GT is greater and LT is less than. And now if both inputs are same, then equals, okay. And if both inputs are same, then equal. If A is 1 and B is 0, and it is greater than. If A is 0 and B is 1, it is less. Okay, so these are the conditions that we can we will see in the syntax formation. So the same way A is less than B and the output will goes to low. So here module comparator in the gate level modeling, the syntax follows with the keyboard module, and the circuit that we are considering is about the combinational circuit, that is comparator, and this is a port list, and the port list consists of output ports and input ports as well. So my inputs are A and B, and the combinations that I am getting is equals to, greater than and less than. And coming to the initialization, port list initialization, so my input ports are 3:0, okay, A and B. So 3:0 means totally 4 bits, isn't it? 4 combinations, 0, 0, 0, 1, 1, 0 and 1, 1. So my output are register equal to, less than and greater than, and always at the rate A and B. Okay, always is a keyword in the gate level model. We are considering, in order to write a particular syntax, we have to follow a specific keyword in the gate level modeling, that is always at the rate A equals to B. And now I am beginning my sentences with the keyword, with the if A equals to B, what happens if A equals to B? Then equals to is nothing but 1 bit, and if 1 bit, if 1 complement B1 equals to, and if it is less than 1 complement B0, if it is greater than 1 complement B0. Okay, so I am writing the combinations here, or else you can write here equals to means B complement 0, 0, less than means B complement 0, 1, greater than means GT, greater than means B complement 1, 0. Okay, this is how you can also represent when it comes to the statements, and I'm ending up with the end, finally with the end module. Okay, this is how we have to write the gate level modeling syntax. This is what we need to follow. And the continuation of here, and again else if. Why? Because here we have to see 3 conditions: greater than, equals to and less than. What if I am considering, if my equals to is this so and so, what if my condition is greater than? So else if, greater than B, and combination same 0, 0, 0, 1 and 1, 0 for equals to, less than and greater than, ending up. Else again one more condition, A less than B, 0, 0, 0, 1 and 1, 1. Here we have considered 3 combinations, right? So n and one more n for one combination, one more n for another combination, and finally I am terminating my syntax with the end module. So this is how we have to write the syntax when it comes to the magnitude comparator in gate level modeling. In the examination, if you find any question regarding write down a syntax for magnitude comparator with respect to gate level modeling, means you have to follow all these things. You have to write all these things without any difficulty. You have to practice it. Okay, first thing you have to mention what is a comparator, and you have to write down the categories, how it was divided based on what, how many inputs, what is the name of the input, how many inputs and what is the name of that, and how many combinations that you are observing. Finally, you have to come up with a syntax followed with the test bench syntax as well in the gate level modeling. Okay, so this is nothing but the test bench code for the magnitude comparator. In the test bench code, we all know that time scale for 1 nanoseconds, okay, or 1 nanoseconds. Basically, we'll consider 1 nanoseconds, and module comparator TST, and register with 3:0 and the initialization of the inputs and as well as the output. Output is via equals to less than greater than, and compare that A, B equals to greater than and less than, and here my combinations for greater than, equals to and less than. Okay, so finally I'm stopping and I'm ending up with this end module. And the binary code for n, the binary code of n digits. So if you're considering any n number of digits for in order to compare, then it used to store in, okay, so this is nothing but the end module, sorry. So it is all about the magnitude comparator. In the exam point of view, you have to write what is a comparator, types of comparator, okay, with the examples. In the examples, you have to write the truth tables, expressions and K-maps, and also in the gate level module, you have to mention what is a syntax, okay, followed with the test bench syntax. So this is all you have to cover up in the magnitude comparator. And one more combinational circuits that we are going to discuss is encoders. Okay, already in the previous session we have discussed what are the decoders, right? And now we will discuss what are the encoders. So encoders are nothing but the combinational circuits. The binary code of n digits can be stored 2 power n distinct elements of the coded information. It encodes. Okay, so n digits can be used to store 2 power n distinct elements. So this is what the encoders and decoders are used for. So for decoding and encoding purpose, these are the combination circuits that is used for. So encoders encodes 2 power n to n bits, whereas decodes, it converts n bits to 2 power n output. So these are the opposite to one another, like multiplexers and demultiplexers, how they are opposite to one another. Multiplexer is many to one, right? So demultiplexer is one to many. So likewise, encoder is nothing but 2 power n inputs to n outputs, whereas decoder is nothing but n inputs to 2 power n outputs. So these are the complement to, opposite to each other. So coming to the encoders, so encoders are the combinational circuits where it converts the binary information of 2 power n outputs to inputs to n output lines. Okay, so n bit code for the input. So for simple encoders, it is assumed that only one input line is active at a time. So for a simple encoders, always remember one input line is always being active. And example consider is binary to octal encoder. So here the example that we can consider is binary to octal encoder, and octal to binary encoders takes 8 input lines and generates 3 output lines. Octal to binary, octa is 8 to binary. So 8 input lines to 3 output lines that we can observe with respect to the octal to binary encoders. So here when you consider 8 by 3 encoders, isn't it? So 8 by 3 encoders. So here we have 8 inputs from D0 to D7 and we have the 3 outputs. So 8 by 3. So here the truth table follows like this. X, Y, Z are the outputs and D0 to D7 are the inputs. So when my all inputs are 0, the output that is enabled when all inputs are 0 except D1. Okay, when my D1 is 1, what happens? My outputs are 0. And when my all inputs are 0, but when my D1 is 1, then the output that we can observe over here, Z output. So here likewise from 0 to 7, these are the combinations of bit with respect to the inputs and as well as the output. So here see, when 0 0 0, okay, when the output is 0 0 0, what happens? D0 is active. When output is 0 0 0, my D0 is inactive. 0 0 1, D1 is active. 0 1 0, 1 is active. So likewise, when 0 1 0, D2 is active and till so on. When 1 1 1, my output, what happens here? D7 is active. So this is about the truth table and the with respect to the the circuit diagram, that is 8x3 encoders. So here the implementation. So how the implementation takes place? The truth table, the output line Z is active when all the inputs are 0 except the octal digits 1, 3, 5 or 7. Similarly, Y is 1 when the octal digits 2, 3, 6 and 7. See, Z means 0, 1, 2, 3, 4, 5, 6, 7. So my Z is active. My Z is active when all the combinations 1, 3, 5 and 7. Okay, for Z 1, 3, 5 and 7. And for X 2, 3, 6, 7. And for X 2, 3, 6 and 7. And for Y, for Y. And for X it is 4, 5, 6, 7. 4, 5, 6 and 7. So these are the particular output with respect to the inputs that we obtain, the activation of the outputs with respect to the input. So here the Boolean functions would be for X, D4, 5, 6 and 7, right? For X is 4, 5 and 6 and 7. So D4, D5, D6 and D7. For Y, 2, 3, 6 and 7. For Y, 2, 3, 6 and 7. So D2, D3, D6, D7 and Z 1, 3, 5 and 7. So hence encoder can release with the OR gates as follows. So this is nothing but the circuit diagram with respect to the gate, with respect to the gates. All these are my inputs D0 to D7 and these are the Y at X is equals to at 4, 5, 6 and 7. The outputs are high. And for Y 2, 3, 6, 7 high. And for Z 1, 3, 5 and 7. The outputs are high. So all these are given to OR gates. So one limitation of this encoder, there is a one limitation for this encoder is that only one input can be active at any given time. So this is one of the limitations pertaining to the encoders. It means that only one input can be active. Okay, we don't see any combinations of the inputs that is to be active, or else we don't see any two inputs are to be active. Only one input are to be active at any given time. If more than one inputs are active, then the output is undefined. So here it says that if more than one input is active, okay, if more than one input is active, that means what? If D1, D0, it is active for one time. If it is repeatedly active, means what happens? It is undefined. X, undefined. And next, for example, if D3, D6 are both active, then output will be 1, 1, 11. Okay, as per this, D6, D3 are active. Output is 1, 1, 1. When, which is, output is D7. To overcome this, we use priority encoders. So, if you are coming up with, or else if you see anywhere, the repetition or else the occurring of the activation of the input lines, if you see any time, then we have to go for the priority encoders. So, as per the priority, the encoders, it will enable or else it will activate the particular input. So, but in the plain encoders, we don't see any, only at a time the one input can be activated, but not the repeated times. If you are finding any such cases, then we have to switch on to the priority encoders. Okay. Another ambiguity raises when all the inputs are 0. And also one more thing is when all the inputs are 0, in that case also we can't able to get the output. That is also a undefined output, Z or X, undefined output. And also in this particular case, encoders outputs are 0, 0, 0 actually. What happens is the output D0 is activated. See, When the inputs are 0, 0, 0, here outputs are 0, 0, 0. What happens? D0 is activated. So, but in some cases, what happens? All the terms will be 0. So here in that cases, we can't say whether it is an 0 or high or low. It's a simple don't care conditions. So in order to avoid this, what happens is extra bit can be added to the output and we call it as a valid bit. So which is 0 when all the inputs are 0 and 1 otherwise. So in order to overcome this, when you observe all the outputs are 0, 0, 0, then in this particular case, we can add a one more extra bit to the output. So that output, that bit is nothing but a valid bit. So which is 0 when all the inputs are 0 and 1. Which is 0 when all the inputs are 0. Or else it will be 1. It could be either 0 or it could be either 1. So that means what? Here we have a chance to add one more bit to the output only when the case 0, 0, 0, 0 when you have. Okay. And coming to the priority encoders. What is the priority encoders? Priority encoders are nothing but these are the combinational circuits. If it has 2 power n input lines and n output lines. 2 power n input lines and n output lines. That means what? It takes 2 power n input data and it encodes them into n data. But here as per the priority, it will encode. Okay, if my outputs are in 0, 1, 3, 4, 7, 3, 2. So as per this, I will be encoding bit 7 first and then goes to 3 and then goes to 2, 1 and 0. Okay, so here a normal encoder which has a problem, that is if there is more than one input with a logic 1, if more than one input with logic 1, with the same logic 1, it will encode the wrong output. Obviously, when my input is repeatedly having 1, 1, 1, obviously at the output, I may get wrong. My wrong output, I may observe the wrong output. So, it works only when the input is high and it malfunctions in the case of multiple high inputs. It just gives only the exact output when one input is high. But if we are saying if you find any inputs repeatedly 1, if you find any inputs repeatedly 1, then what happens? It obviously shown a not care condition, don't care conditions. Okay, it malfunctions. That means what? It gives the wrong data, obviously. So in order to solve this, we are going up with the another encoder called the priority encoder. So we prioritize the level of each input. As I said we prioritize the level. Okay, we prioritize the level. As per the high level, we will be encoding the particular bits. Okay, we prioritize a bit and as per that we will encode. So if multiple input lines are selected, the output code will be corresponds to with respect to the input, which is highest designated priority. So particular input, if we want to encode the particular input, and if that input is having the highest priority, that means what? If for suppose I'm having A0, A1, A2 and A3. Okay, these are my inputs, and for these inputs I'm given 7, 2, 0 and 1. So as per this, I can now encode my first input A0. Why? Because it is having the highest priority. Okay, the number is designated high, so I can encode it first, and then comes up 2, and then comes up 1, and finally 0. So it is nothing but the priority encoder. As the name itself indicates that as per the priority given to the inputs, we can encode the particular bits. And this is all about the syntax, module, priority encoder, and my inputs are 7:0. That means what? 8/3 encoder. In 8/3 priority encoder I am considering. Okay, my inputs are from 7 to 0 means 8 bits. A. And here initialization of the inputs and as well as the output. So input A70, B, C, D, and we have selection lines and output with register 7:0 output. After initialization, always at the rate. Always is a keyword given when you write in the gate level modeling. Remember that always, and also in the behavioral modeling, we can write this always at the rate A, B, C, D or selection, and now begins if else. Why? Because here we are writing the combinations, right, based on the priority, based on the combination of the inputs and outputs as well. So in the case like we are selecting, if selection lines are 2 0 0, if my selection lines are 0 0, output is less than equals to A. If my bits are 0 1, if it is 0 0, less than or equals to A. If it is 0 1, less than or equals to B. If it is 1 0, less than or equals to C. If it is 1 1, less than or equals to, if it is 1 1, less than or equals to Z. So based on these conditions, I am writing my statements with the if else conditions, and finally I am ending up with the N and terminating my whole syntax with the N module. Okay, this is how we have to write the expressions with respect to the encoders. So this is all about the today's presentation. That means we have studied, we have learned something about the Mangroot comparator, encoders. Okay, different types of Mangroot comparators based on the inputs that you are considering, 1 bit, 2 bit, 4 bit, and also coming to the encoders. What is the encoder? It's a contrast of decoders. And what is the priority encoders? What happens if the number of if the inputs is the state of the input is repeated? Okay, 2 or more than twice. Only one time the input is to be considered only one time. But if my inputs are repeated twice and thrice more than once, what happens? Based on the priority, based on the designated number given to the inputs, based on that I'm going to prioritize and I'm going to encode the particular input. So this is all about the encoders and Mangroot comparators. So it is a part 2 of the combinational logic module. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.